Hey, what's going on, folks? It's Mike here, and welcome back to my programming language first impression series. A series in which we take a look at a programming language for the first time for about an hour or so and just, well, experiment, see what it's like. Now, today we're breaking that rule a little bit, and we're going to be taking a look at, well, the second hour with the Mojo programming language. So if you haven't seen the first part of this, I'd recommend checking that out so you can get a feel of what the language is about, its origin, and where it's sort of coming from, and some of its design goals. Talk a lot more about that in the first video, and I'll put that linked below, or you can find it in the playlist. So otherwise, let's go ahead and just dive into the language. We're basically just going to go through the getting started page here. So get started with Mojo. This is where we started exploring last time, and we got to see like the very basics of just doing a build here. But I want to take a look at this sort of left side here, so we can look at some of the things like the ownership, traits, what pointers look like, and let's say if we can get to the GPU programming, that would be a good start here. And then maybe we'll want to at least peek at some of these other sections here, like the interop, because again, this is basically a superset, as I imagine, or Python is a subset, or portions of it perhaps are a subset of the Mojo programming language. So if you want to follow along, the Compiler Explorer tool, Godbolt, has Mojo as an option, which might be interesting just to see from a code gen sort of perspective, because we talked a lot about MLIR in the first video, or at least a little introduction to that. And again, the key idea with Mojo being this language that can sort of mix or do heterogeneous computing, but make it more seamless, right? It's just in the language here where we can program on multiple devices. So anyways, that's one thing we could do. Otherwise, I think if you go to the home page and then resources and Mojo Playground, you might want to just play around with the examples here. You could just go to run and run the little hello world if you don't want to install or can't, for whatever reason, install on your particular operating system. So anyways, let's just go to the getting started. Again, you're going to see me do this for the first time and just kind of explore the language here. We've done the overview again for getting started, getting our hello world up and running. I'll move that. Let's just move this window to the side here. Just so we can see more. So let's start looking at variables. I mean, we have created some variables here. And I guess there's different ways to do it here. Now, if I do something like name2 equals, we're just going to keep doing Mike here for the names here. Let's see. Oh, and I put in an illegal. I was just playing around with something there, but let's try that again here. Yeah, okay, so this is a warning. Oh, this is interesting. I mean, so, right, so the difference here, I mean, I can specify the var, or I can do this, and it's going to kind of work like auto, I guess, in a language here, where I don't need to specify the type here. It's just going to probably assume that as maybe a string or whatever a reasonable type is. You know, C programmers, maybe we're thinking of this as like a const char star or something, but I'm going to assume it's going to take a string type. So that's kind of interesting. Now, this is interesting from the build system, right? We're building our file here using Mojo build and then passing the file, and then I'm just going to run the executable. Again, Mojo, as we saw in the last video, has a REPL as well. So again, you can get sort of the best of both worlds with just interpreting your code or building it on the fly, I suppose, and this and compiled code for the speed there. But anyways, this is kind of interesting, this warning here. So we are getting interesting stuff. So name was never used, assigned to underscore again instead. So it is interesting just to see in the language some of the compiler errors and warnings. So anyways, we'll keep an eye on that and we'll fix that. But again, I just wanted to show that you don't have to specify the types there and they'll be inferred, but this is a statically typed language here. Okay, so we can just assign a value here. We can explicitly declare variables with the var keyword. I kind of like that. It's a little bit more greppable, and you can see sort of where the lifetime of a variable starts, right, with a declaration. And then we can also add the type with or without an assignment here. So here's an example of just the type, and here's the assignment. And I wonder if this has default types, like is some going to be 0 here? That would be kind of interesting to know if it has a default value. But either way, let's see. Both implicitly declared and explicit declared variables are statically typed. That is, so again, that means when this is an int, it's always an int. Okay, there probably are types or maybe a library where you can have things like a variant or something that can take on multiple types. But anyway, statically typed languages are typically safer, right? You know what the size of something is when you debug it. You kind of know what the type is, so that's kind of a nice thing. So again, the type doesn't change at runtime. Okay, so kind of nice. You know, I would say programming documentation these days, especially in a lot of the languages that we've looked at. And this is also actually a really important reason to take a look at other programming languages, I think. Like coming to mind, like we looked at Odin and Zig and Rust and some of these other languages. Their programming manuals often talk about a lot of nice stuff like this. Like this paragraph is just, these two sentences are just kind of important, and you don't sometimes see those in introductory tutorials online or programming books, sometimes on intro programming books, and for good reason. Maybe they're not necessary, but again, this is telling us exactly what is going on here, so it's kind of neat. All right, so anyways, and then this is demonstrating the example. I don't know, maybe you folks read programming books when you're first learning that taught you this stuff, or maybe I just forgot, but that's kind of nice. Anyways, I'm just saying this is nice documentation. All right, so for more details, see the page about variables. I do actually want to see if they are default initialized. Initialize, let's see here. Here, user ID variable has a type but is uninitialized. Let's see, implicitly declared variables. So I wonder if, let's kind of look here. So this is just talking about the initialized. I guess, I mean, for speed purposes, it would make sense, right? This is sort of the C++ approach where you don't put in a value here, right? This could be like garbage in this value. We could just print it out. Let's just see what happens, okay? And let's use var int something like that, and then and let's just make it, var random, let's just say a number. How about that? So let's see, do we get garbage or do we get 0? This will be an okay test because sometimes it happens to be 0. Okay, error, use of uninitialized value a number. Okay, so it's actually just an error. That's kind of interesting. So if I do initialize it to 0, ooh, I kind of like that here. Okay, then I get 0 printed out, and then I run the rest of my program. Now if I want to uninitialize it, is it just the underscore here? Error cannot read from discard. Oh, that's a discard thing. Okay. So I wonder if there's a way to do an uninitialized value, because if I have like a list of, or like a static array or something, I might not want to initialize it. There must be a way here. Let's see here. Late initialization. Okay. Using type in the annotations. Oh, for example, notice the z variable is first declared with just a type, and the value is assigned later. Hey, so that let me do it here. If you try to pass an uninitialized variable to a function or use it on the right side of an assignment, compilation fails. Oh, I see. So as long as it's been initialized somewhere, it's okay. So I can do this, but as long as I go a number equals 10, that's okay. Interesting. So a smart compiler. I mean, I guess if you're going to have the whole ownership system and stuff, you can do this sort of static analysis. This is a pretty easy thing if you're doing sort of a data flow analysis to say, I've seen this thing here, and then when I trace where I've used it, what functions I'm going to pass it into, and see, has it been assigned at least one time, right? Is there some assign expression or something in the compiler before you actually use it, right? So this is like a use, what would we call this? I don't know. I mean, it's just the uninitialized variables, but it's some sort of use before assignment, probably flag or something like that. Okay, so anyways, we got variables, and there's a bunch. Let's see where this landed us in the documentation here. Okay, we're still in the variable section here, but we want to stay in Mojo basics, but there is in the variable section. I guess that's where we are. All right. Anyways, blocks and statements. Let's keep moving along here. Okay, so we got scopes, and as we discovered last time, since this is sort of a Python language here, we do have to use indentation that is meaningful. Some people love that, some people don't. I indent my code anyways, so it doesn't really matter in any language I use. You just have to be consistent and make sure your team is using spaces, right? That's not controversial for me to say. So 4 spaces here. All right, anyways. All right, so all code in Mojo, all statements end with a new line. Statements can span multiple lines with your indentation. Okay, for comments. Okay, so that makes sense. Or actually for this string here. Yeah, that's fine. Okay. And you can chain stuff. Okay, yeah, chaining, that's nice here. Let's do a little something interesting here. Let's do our greeting and then do greeting.join. Hi, you are awesome. Let's do something like that. All right, let's rebuild our program. Warning, string value is unused. Interesting. Okay, because I gotta assign this, right? Greeting. Let's reassign it to itself and see what happens. All right, so built. Who am I? Mike. You are awesome. But I guess here I should do greeting plus equals or something. Let's see. Is plus concatenation, or is there some other symbol? Mike. Okay. Hi, Mike. You are awesome. Okay. Yeah, that's neat here. Okay, so let's see if we can find some other functions here to chain to this. But I guess we could just use join. Again, .join. Is this going to work here? You are awesome. I agree. Okay, something like that. Just trying to get the indentation rules. Again, I haven't. I gotta update my Python here. Hi, Mike. Who are you? Oh, hi, Mike. Oh, greeting.join. Hey, this is kind of an interesting semantic thing. I guess I can't join twice here because I get the hi, Mike. That's written in a memory, and then if I do .join, and then .join again. I wonder if I have to allocate the string here. Okay, let's see how this works here. String, something like that. Okay, they were careful to do that. Let's see if that example works here. Oh, inconsistent. Uh-oh. Oh, boy. We're going to run into tabbing errors here. Okay, anyway, let's get rid of that. But keep an eye on that as just kind of an interesting thing here. Anyways, you can do chaining with the dots. Maybe I'll just put them on the right here rather than fight our text editor here. But that's nice. I really like this. Again, when I'm using D, uniform function call syntax is one of my favorite things here. So in other languages, JavaScript and so on, Python, etc., have this feature. All right. Functions. You can define Mojo function with either the def or the fn keyword. Okay, interesting. I wonder what the difference is. For example, the following uses the def keyword to define a function name greet that requires a single string argument and returns a string. Now, again, since this is, again, from Chris Latner coming from Swift, I seem to recall something of this sort from Swift. Again, I haven't touched Swift in a while. Or maybe was it a different language? Maybe somebody else can remind me here, but I guess you get both. That's kind of interesting. Okay, so I can do def. I wonder... Okay, where def and fn are different is error handling. And argument mutability defaults. Okay. Interesting. Yeah, I knew there was some difference. And I'm trying to remember, because we looked at least one other language in this series where that was the case. So I'll have to try to remember what that was. Unless I just had a dream or something that I was already using this language. Okay, so both def and fn are function declarations, same concepts. So I wonder if I wonder if this is part of the interop story with Python, right? Because this is how we do it in Python functions, and maybe fn is the different defaults here. So let's see here. So def and fn comparison. Brilliant! I don't have to read the whole thing. There's a nice section here for me. Okay, they have much in common. You declare the type of each function, the parameters and arguments. If a function doesn't return a value, you can either omit type or declare none as the return type. Okay, so again, I've got the trailing and return types here. If the function returns value, you must declare either the return type, okay, or provide the named result. Okay, that's fine. And I can have out parameters for that. That's also works. That's also kind of nice. I actually kind of like this syntax here. Now I wonder, just something with out parameters. I wonder if that's an interesting, when you have interop with other languages. I mean, out, basically like in C or something, when you have an out parameter, you just make this type like a pointer or something, right? So, all right, let's do a little block, I don't know, a little comment here or something. Right, in C, you'd have some void like function, and then you could have like some, I don't know, let's just say you have a some values here, and then you'd have a output parameter here, right? And you'd write the result out in some pointer like this, right, to store the actual result somewhere. And then, of course, you need to make sure that you've allocated this somewhere, and its lifetime, et cetera, is going to be there. So that's kind of interesting. I wonder if it makes for a better interop story to have these sort of out parameters with not only C, but maybe other languages. That's something to think about. It's interesting. I mean, in and out itself, I think, of a few languages where you have like a out qualifier in the type shows up. I mean, these show up in graphic shading languages for sure. They show up in other languages like D and so on. And they're kind of nice for the documentation. I guess that's the purpose here. But all right. Anyways, it's just kind of a little aside here. Let's get rid of that so it doesn't distract us. So where are these different? With defining a function in fn differs in error handling. Okay, the compiler doesn't allow a function declared with fn to raise an error condition unless it explicitly includes a raise declaration. Interesting. Okay. In contrast, the compiler assumes that all functions declared with def might raise an error. Okay. So we would say maybe in C++ parlance or something. Okay, so the compiler doesn't allow a function to raise an error condition. So this is going to be like a no except type of thing, which is sort of what you want. And this has to deal with, I guess, again, how the compiler is going to handle errors, right? Because the function could just return an error code. I mean, you could do that with either one as part of the return value. But having some information about, is this function going to break control flow with an exception, right? If you throw something or raise an exception, it's kind of interesting. So that's kind of interesting. Yeah. Let's just take a little peek at that raising and non-raising functions, right? So you raise an error, okay, which I'm thinking of like throwing an exception in other languages. Yeah, interesting. Okay. All right, so let's get back to our functions here, and where we were in our basic language. Okay, so for our matters, I think getting started here, it's not going to matter so much, but let's continue on. So comments, okay, it looks like we got the same comments as in Python, and then you have your API or documentation strings, which I think this is a really nice thing for a lot of languages to probably just adopt the triple quotes. Just make those doc strings. I think that's one thing the Pythonic languages really got right. It's pretty simple. And then you can have some keywords on a line here. That's like the simplest thing. You know, I like Doxygen and stuff. I use that with, you know, C++ and D, but this is easier. All right, anyways. Structs. All right, you can build high-level abstractions for types or objects as a struct. Okay, struct in Mojo, similar to class in Python. You can both have methods, fields, operator overloading, decorators for metaprogramming. How exciting! I'm actually looking forward to when we get to that. And however, Mojo structs are completely static. They are bound at compile time, so they do not allow dynamic dispatch or any runtime changes to the structure. Mojo will also support Python-style classes in the future. Okay, so still being worked on here. I guess they'll figure out. But yeah, this is something I've seen more frequently, and I guess we're going to eventually uncover Mojo has traits, so that's a way that you can sort of like fake inheritance. In D, we have things like mix-ins where you could do that if you want to inherit some structure. D has structs and classes, but a lot of languages have opted sort of for just having structs as sort of a value type to avoid inheritance and just say, hey, this is just a chunk of data. And then basically with a little bit of, you know, the compiler magic, so to speak, you can just have these, you know, your constructor. I suppose this is a copy constructor, maybe copy initializer, yeah. And then whatever, you know, functions you want here. And okay, this is looking pretty Pythonic here. You have the self object, which is an out parameter, okay, and then whatever other arguments that you want here. Now this is kind of an interesting existing self here. Again, it's been a little while since I've done object-oriented programming in Python, so I'll have to refresh here. I'm going to refresh at some point here. I sort of Google my way through Python these days since I don't use it as much, but this is kind of interesting. if that's new stuff. And here's how I can use it. Okay, so if we're creating my pair here. All right, let's write a struct here. Let's just say, okay, my pair. And this is interesting. Copyable. Is that a trait or something? Var first int var second. I'm going to make this a string just to play around with it a little bit. And then let's use fn, which we know does something with the immutability of these things. Out self, I'm just going to mimic this here. First is an int, and then again we've got the types after, which will probably take us some getting used to, but I don't mind it. And then a colon at the end here. All right, let's just see that that's one line. Enter, some tabs. Self, so we got to put self in front of everything, right? In Python, that tells us we're referring to the instance of this whatever object we initialize here. First equals first. You see I hit that semicolon often, but we don't need it. All right, so let's do something like that here. Make sure we're compiled. Let's just see if we write out this object what happens, or if we have to write a dump function. So again, my pair. Let's see again. Let's see. Var test. Okay, that's going to be of type my pair, and I need to initialize it. Call the constructor 5, and then Michael, just to have something differently. And let's try to print out test without the dump function. I'll rebuild it. Let's see, error, expected a type, not a value. Okay, let's see what I did wrong. Var, I pair. Oh, I just have to do equals right there. Okay. Let's see. What have I done here? Do I need the function? I've got the out self here. Okay, invalid call to print. Oh, okay, yeah, it doesn't want us to print this here. Let's see what kind of error messages we got here. Invalid call to print. Okay, failed to infer parameter. Okay, so this must be t's. When I see t's, that must mean print is like a variadic function. So that's t for the type, and then s means like multiple of those. That's probably what it is. All right, let's see if I write that little dump function, what happens. Def dump self. I guess that's just going to be an overload for us to format. Print self dot first, self dot second. Okay, let's see. Did that help us? I don't know if that helped us here. Okay, maybe we can't use it with print. We just got to call test.dump. Fair enough. Oh, and I'm going to keep putting semicolons at the end. My bad. All right, well, let's see here. Okay, 5, and then, Michael, for example. Right. Okay, great. Okay, so we have mastered structs, sort of, but seen a few interesting things here. Now, I put in this copyable, and I don't know, I didn't define the, what is sort of the copy constructor, but probably a better way to think of it, and a better name, and again, I can't remember if this is a Python thing, but copy initializer, or copy initialization, seems like a better thing here. Let's see, I'm sure the documentation will help us. It's been guiding us well so far. Okay, so again, note that some functions are declared with fn function, while the dump function is declared with def. In general, you can use either format a struct. Okay, and then we've got these two things. Okay, the constructor and copy. Okay, it is copy and constructor in this language here. Lifecycle methods like this control as struct is created, copied, moved, and destroyed. Okay, for most simple types, you don't need to define these. So like in many other languages, like in C++ and so on, you get these for free. They'll just do the bitwise copy here, which is this at fieldwise init decorator to generate the boilerplate for us. Okay. And Mojo will synthesize copy and move constructors if you ask them with trait conformance. Okay, so the myPair struct can be simplified to this. That's kind of cool. So copyable, that's going to give me the bitwise copy constructor. So yeah, my copy was basically just icy from the existing. That was the name of the variable, right? And I keep forgetting that those things are inferred. Self refers to myPair. Okay, now I get this full. Well, I've got it translated to C++ in my head because that's usually what I'm thinking in when it comes to object-oriented programming. Yeah, we can just put copyable and movable. That's kind of nice. I like this. I think this is a good thing in languages. And again, you can do this. Other languages will do this. Like, again, think about C++ or maybe Java or something by just inheriting or having some like interface here. But I guess these are the decorators here that you're adding here. Okay, so very, very neat, very fun stuff. Okay, let's see where we are in the tutorial. We're down to traits. Okay, so getting into interesting stuff here. I mean, it's all interesting. But let's see, traits, this is an exciting thing. And folks talk a lot about the trait system in Rust, for instance. But let's see how it is in Mojo. So a trait is like a template of characteristics for a struct. Okay, nice way to describe it. If you want to create a struct with the characteristics defined in a trait, you must implement each characteristic. Okay, so I'm also thinking of this like a interface in other programming languages. I wonder if there's a, maybe the interface, because we're more thinking of interfaces in other languages as sort of like it's almost like a is a type of thing, like with inheritance, right? So for instance, sorry to go on another tangent here, but I think it's important. So let's put it in the comments, right? And if I create an interface, and again, I'm thinking in like D here, and I call this like animal or something, and then I have a class, cat, and it's going to implement this interface, right? Then I can add all the, let's see, the classic, like, I don't know, walk or something, and then I gotta do override, walk, and then, implement this thing. But I think the difference here with interfaces is, right, then I can instantiate a collection like this, animal, and say my animals, and it can be anything, that is, part of this interface, right? So that's the more like polymorphic type thing. Traits, I think, are characteristics, and let's see if I'm right here, where, I can have this trait here, and I would do it like animal actions or something. I don't need to override it. I think I just need to probably implement it. But I don't instantiate a class of like animal actions. I basically just have my cat, and it does animal action things like walking and talking and so on. And then, of course, in Mojo, we have no classes but structs. So you don't have that like dynamic dispatch or runtime polymorphism to choose the right method for the right type that it's instantiated as. That's what I'm kind of thinking of this as here. Let's see if I'm right here. Because the other way to do this in D would be with a mixin, which is just effectively copying in this code here to a struct, because you don't have sort of hierarchies with structs here. There's no inheritance. Okay, so yeah, each characteristic in a trait is a requirement for the struct, and when your struct implements all the requirements, it's set to conform to that trait. And that's kind of nice. I think it's actually a well-named thing in programming languages. I wonder where this originated from. Again, since we're looking at newer languages, I think Rust made this quite popular because I keep hearing about it, and everybody likes the trait system. But I think it's a nice thing. So again, if anybody knows where traits were first popping up in programming languages, that would be interesting to see. And hopefully we haven't covered that language yet, because then I just missed it, which could happen. We don't always make it all the way an hour. Anyways, using traits allows you to write generic functions that can accept any type that conforms to a trait rather than accept only specific types. Okay, interesting. So for example, here's how you can create a trait. Okay, trait, some trait, and it has this required method. And the three dots following the method signature allow Mojo syntax indicating that the method is not implemented. I see, okay. Here's a struct that conforms to the trait. So again, I'm going to do the field-wise initialization. So that gives me that copy constructor for free, I guess. Struct, and then I say, hey, I want some trait here. And then I have to implement it, okay. Then here's a function that uses the trait as an argument type. Okay, here's a function that uses some trait here, and then it says, okay, oh, interesting. Let's play around with one of these at a time here. Okay, so let's get rid of our little experiment. And okay, let's just start with writing our first little trait. Some trait, function required method. Okay, and it's going to call on. This is a method itself, and I can do the, dot, dot, dot to say that it's unimplemented. Okay, great. Okay, so now let's create our struct, field-wise init. Okay, so that makes our our constructor, I guess, trivial, or maybe our copy constructor. We could maybe even make it copyable or something here. Some struct. Let's just follow this example. Just gonna take in some trait, and it needs the required method here, and I'm gonna match the signature, and just print this out. Hello traits. X, sure. Okay, so this builds. That's good news. Let's see how we use it. Here, let's hide our little my pair example. Let's actually comment out some of this stuff here, just so we're getting new stuff here. We'll just hide those in folds for now. Okay, and let's actually do some struct, something like that, and okay, we gotta test. Then I gotta initialize it. Test equals. Oh, let's just do it like this here. 5. Okay. Oh, bunch of errors. Let's see what I did here. Okay, unterminated. Oh, did I just not put a quote here or something? Here, I can just delete all this. There we go. Let's save it. Invalid initializer expects at most 0 positional arguments, got 1. Now wait a second, I did say, oh, that's for a required method here, right? Okay, all right, and I just did my field initializer. Okay, so now I should be able to call test on the required method and 5. Okay, and it'll print that out. Hello traits, spelled wrong. All right. Okay, something like that. Okay, now let's look at the function version of that. That's kind of interesting. So fun with traits, so some trait. And I guess this is just saying whatever type I call, I see when I talk about generic programming here. So whatever type that I'm going to pass in, this is sort of acting as a constraint that it needs to be able to, whatever this object is, have required method here. Okay, so in C++, right, we have concepts for this. In D, we also have like things like compiles to see if this is like code, for instance, and you can put a template constraint. And in this case, we just use the trait system here. So that's kind of cool. That's very cool. So function fun with traits. So whatever the type is, let's see, I need to be able to do some trait. Okay. Make sure I spelled everything right. And then let's say x dot required method 42. Okay, so now I should be able to say fun with traits, and then pass in this test object, and it will call on that test object the required method because it satisfies that trait here. Oh, excuse me. All right, perfect. All right, we figured out the trait system, and again, kind of nice to make that connection with things like concepts in C++ or template constraints in D, and maybe other things in other languages. It's sort of like a contract. I've used some variations of other languages that have this as sort of like a contract. I mean, it could almost be like a precondition, but this is checked at compile time because I'm assuming the brackets, again, are like the generic programming that we have here. Okay, so that's cool. And the type of stuff that you'll have here are, I mean, I guess you could have a huge range of stuff here for like the traits, like is iterable. I mean, I think about these for like iteration or like ranges and stuff to see like, can I go iterate through some data structure in a bidirectional manner, meaning forward and backward, or is it a forward iterator? These types of things are things that I tend to think of immediately. But again, you could have traits for all sorts of stuff. Now I wonder how far I can go with this if I do have like contracts where in this trait I can put some sort of constraint, like where it has a property or something. That would be kind of interesting. Because and why I'm saying that is I'd want to see if it has like some trait like a static size of the container or something that's small enough so that I could do something like call the function that works on small arrays or something, or the big arrays function, or whatever, would be kind of interesting. All right, anyways, you'll see traits used a lot in the Mojo library. Mojo's collection types like list and dictionary can store any type that conforms to copyable and movable traits. Okay, so yeah, that's getting in this like, is this type copyable or movable, right? Does it have those special member functions, defined, or special member methods in this case? So that's pretty cool. Okay. All right, you can specify the type when you create a collection. Okay, that's cool. Float 64. Another trend in programming languages that I've seen is defining the type and the number of bits with it. I sort of like that, actually. It's just more specific. And this takes care of a lot of problems, like, if I asked you what the size of an int is in C, plain old C, right? Most of us say 4 bytes. That's kind of the standard, but it could be 2 bytes. You just never know. So, you use your fixed width types if you can. So that was something nice. And D just has standard type. And this, and Mojo and Rust, I believe they also just have like, here's how many bits you have. Which also I recall from my LLVM IR writing days, where you have the types and sizes, or if you've done assembly, you kind of know the size of things based off of the suffix of the instruction. So anyways, without traits, the X argument would have to specify it. Okay, we get it. All right, parameters. Mojo, a parameter is a compile time variable that becomes a runtime constant, and it's declared in square brackets. Okay, so this is basically that answers that question finally of this in our code is basically like, yeah, our template parameters or generics or these types of things here. Okay, so many other programming languages, use parameter and argument interchangeably. They do, and I accidentally make this mistake too. So be aware that when we say things like parameter and parametric function, we're talking about these compile time parameters, whereas a function argument is a runtime value that's declared in parentheses. I actually like that, okay? That's a good way to remember it. So parameters are compile time things. Let's sort of say that, right? When you document, right, often you'll see at param, right? So that's what you're documenting. And then arguments, again, usually in your main function, you have like args or something. Although this is empty, so in C, let's say you have your arg count and arg values here. And of course, this is a count. So again, maybe just a way to remember that as, things you're actually passing in, that you're actually getting values at runtime. Okay, so I'll try to be more precise in my parameter versus argument usage. Okay. Anyways, complex topic that's covered in metaprogramming. Well, that's okay. We could take just a little peek, I think, at the metaprogramming here. But let's see what we got here. So this is going to be a repeat function here. Yeah, okay. We'll do it right here. Little repeat function. Let's see here. Define, repeat. And then here's our parameters. Count how many times to repeat. So this is a compile time. This is just going to get compiled down to a constant, so that's to be something that we can know at compile time. And then the string. And then at parameter. Oh, this is interesting. Evaluate the following for loop at compile time. Okay. So that's what this annotation is. I mean, all the annotations with the at symbol are saying something, right? We use that here with the field-wise init here. But okay, so we want to do this loop here. In D, we have static for each. In other languages, you have that. But this, we say for I in range count. And then pragma. Again, speaking in D. Print message here. Okay. So this is kind of nice if print should just work. Some languages have like special like compile time prints and stuff that you would use, but this seems like it'll just work here. So let's put this towards the bottom of our program here, and let's see if I do. Now this is gonna evaluate this. Let me see here. This is just gonna generate the function. It's not actually gonna do anything at compile time, is it? Let's see here. Let's just call repeat 3 times. Hello, YouTube, something like that here. Yeah, maybe there is a compile time print function, but this is going to generate the code for us here. Actually, here, let's leave that typo in and see if it gives us a good error message. Use of unknown declaration. Okay. So sometimes some languages will use like the Levenstein distance or something and give you a suggestion here of symbols that it's found. So that's another error messaging thing. Hello, YouTube. Okay, so simple enough here. Okay, but yeah, it's generating this code at compile time or telling it how to sort of unwrap this, and then we'll call this function at runtime. I wonder if there's a way to just put like at compile time repeat or something. How do I make this run at compile time? So anyways, that's the metaprogramming story, but this is a super useful and seems like a super easy thing to use here. Again, maybe I never got far enough in my Python days to see if there was something like this for the generics. I guess, let's see, if I just bring in another Google window, Python metaprogramming. Okay, here's somebody's guide here. Okay, I have like decorators and stuff, meta classes. Okay, so you have some of this and these through decorators, maybe adding stuff, but this seems pretty clean in Mojo, how to handle this. Okay, cool. Okay, some other stuff here. Okay, so we're doing pretty good on time. I think we're going to make it in under an hour, maybe. Famous last words. Let's see, Python integration. Okay, so Mojo supports the ability to import Python modules as is, so you can leverage existing Python code right away. Awesome. So I can just bring in, basically my whatever I want here. And I've got the same sort of from symbols here. Let's do it. Let's follow along. And take a look here. And let's bring in, what do I bring in NumPy library? MP Python import module. Okay, so I guess it's executing some Python code here. Let's see, it looks like we're making an array, 15. And 3 by 5 for the dimensions, and let's print it out. All right, so we're gonna get a nice, what are we gonna print out here? The values here, grid. Let's see, I'm gonna run it. Unhandled exception. NumPy has no attribute or range. Oh, a range, that's because I spelled it wrong. That's pretty interesting though. Did this bring this in at runtime then? So this brought this in. I mean, this is like loading a shared library or something. Then we didn't get the exception until the end, so we could try to catch that or something, but yeah, let's try to do it properly here. So that's kind of cool here. And yeah, there we go. We get our little printout here. We're 3 by 5 or 3 rows by 5 columns, multi-dimensional right here. Okay, neat. Pretty simple. Okay. All right, next steps. Hopefully this page is giving you enough information to start experimenting with Mojo, but it's only touching the surface. Yeah, I think so. Okay, so we made it through the bottom here. I do want to take a look at the ownership and then maybe the pointers and GPU stuff before we leave. But overall, I mean, just looking at the language here, and modules and packages, the core of the language here is pretty neat and simple, so to speak here. I mean, it's structs, functions, variables, loops, other stuff that you're familiar with. So a nice little getting started guide here. And the language itself is pretty simple. We're getting pretty decent error messages. The trait system's really cool. You can see how that could be very, very powerful. So there's really no limit with this language here. But ultimately what we want to get to is some of the more powerful features here. So let's just take a look at the intro to value ownership, which I guess is going to be some sort of borrow checking thing here. Let's see. So program is nothing without data. That's true. Right? We're just transforming data at the end of the day on our machines. And all modern programming languages store data in one of two places: the call stack and the heap, and the binary as well, I suppose. But yeah, call stack and heap we think of. So also sometimes called in the CPU registers. Yeah, okay, yeah. We're not going to get on all these things here. Yeah, CPU registers and the binary and cloud store. I mean, we're storing stuff all over the place. But anyways, any language needs to read and write data a bit differently, sometimes very differently. Okay, so let's see how we arrange stuff. Okay, so stack and heap overview. Again, nice programming documentation here talking about some of these things that you don't see in intro tutorials here. So again, really nice. Even if you're not going to use Mojo, it might be worth it just to read the documentation or, some of the languages that we've looked at in this series, because they really do a nice job explaining how the language works. And that's ultimately a nice way to learn about programming and computation in general. Okay, so this is just talking about the binary and stack and heap stuff. Have some tutorials on that on my playlist. If you want to check that out, just search, my name and stack and heap. All right. So anyways, this is going to talk about some memory management strategies, and I'm seeing words like garbage collection. D by default is garbage collected, but not limited to it. Java by default is garbage collected. C# garbage collected, and then there's manual memory management languages like C and C++. And then, of course, we've got Rust and I guess Mojo here using a third approach called ownership. So I think this is going to be closer to a Rust style thing here. So again, let's see here. And I don't know if it's using like reference, count by reference, or reference counting, semantics, but let's see here. So Mojo uses a third approach called ownership that relies on a collection of rules that programmers must follow in passing values. Okay, the rules ensure that there's only one owner for a given value at a time. Okay, and then when the lifetime ends, Mojo calls its destructor. Okay, so that is maybe sort of like a reference counting thing. Let's see here, but also with a ownership model here. Okay, but first we need to understand value semantics. Okay. All right, so value semantics are like values. Let's just try to look at a quick example. This is really nice. You'll want to read this whole thing. We're trying to get through this in under an hour and get to the GPU stuff. But this is a pretty nice. This is pretty nice for a few reasons. One, because they're going into a lot of depth here, so you can understand exactly how this is working. The second thing is, again, it's very clear that this sort of model is becoming a nice approach in terms of memory safety. But I also wonder, having this ownership model, how important it is to, if I'm programming for multiple devices and transferring data from CPU to GPU or AI accelerator or whatever, you kind of want that data in one place or to know who owns it. So again, this might just be a necessary part of the language, which is kind of interesting. Okay, and we got some comparisons here. So let's maybe just try an example here. We're going to kind of jump around here. This is kind of interesting. Maybe this is the insightful, and then we'll try an example. So Mojo's read is okay. So reading in Mojo is kind of similar to when we pass values const reference, right? So we don't make the copy, but it's read only. Okay, that's what that means here. Okay. But it's different in C++ in two ways. The Mojo compiler implements a lifetime checker that ensures that values are not destroyed when they are outstanding references to those values. Okay. Small values like int, float, and SIMD, okay, which could be the vector register type, are passed directly in machine registers instead of through an extra indirection. This is because they're declared with a at-register passable decorator. Interesting. This is a significant performance enhancement when compared to languages like C++ and Rust, and moves this optimization from every call site to declaration. Oh, that's interesting. Okay. So again, something that we can learn taking a look at this language here, that you're just putting the arguments passed in directly in the registers. Okay. For small value types. Interesting. Okay. Perhaps to some limit or as many as you can fit, if you're passing in, say, only 5 arguments or something, that works. But yeah, this is kind of interesting. So the major difference between Rust and Mojo is that Mojo does not require a sigil on the caller side to pass by immutable reference. Oh, interesting. So Mojo is a little bit more relaxed, I guess. Also, Mojo is more efficient when passing smaller values because of maybe this machine register optimization. And Rust defaults to moving values instead of passing them around by borrow. I see. So yeah, Rust transfers the ownership, and Mojo has this borrow, I guess, where maybe, is it reference kind of? We'll have to read into this. This is interesting here. So it's just kind of easier to use, or maybe less strict in the name of performance. So interesting. I mean, again, this would be an interesting language. Hopefully this is interesting for folks who are going to read through this, and feel free in the comments to clarify if I've missed an important part here, because I'm just skimming this for the first time for 2 or 3 minutes, but it might be an interesting follow-up discussion here on the actual language to see how this works. So, all right, let's just look at some examples here about what's different here. So mutable arguments. If you'd like your function to receive mutable reference, add the mute keyword in front of the argument name. You can think of this like this. It means any changes to the value inside the function are visible outside. Yeah, it's mutable. Again, we think about this like a passing in a reference in C++, right? So I can change this list here. This one I don't pass mutable because I'm just printing the list out. But this will actually append 5 to my list here, okay, which we see in the results here. Okay, neat. That behaves like an optimized replacement for this. Okay, otherwise you'd have to return a copy, right? So again, the classic thing, you don't want to pass in a super long list here and then have to copy all the values and then append and return the copy, right? You just mutate the actual thing you want here. Okay, so some nice stuff here that everybody should know about. All right. Transfers. Okay, so we looked at this in the first video just a little bit. The owned and then transferring the ownership here. Which again, I kind of made the analogy in C++ of like a unique pointer of passing in a function here. So let's just take a look at this example here. So take, if I call this function, it's going to pass it in this string, and then this function owns that string, so to speak. Now it doesn't do anything with it. So I guess that string will just get its destructor called on it or something and get eliminated. But let's see here. All right, transfer. Oh, is that how you call the sigil? I just call it the caret, but transfer sigil. Hopefully I'm pronouncing that correctly. It ends the lifetime of that variable. I see. Oh yeah, okay. So anytime I'm seeing this word, I'm thinking of Doom. Let's see, the video game with the recent release from John Romero, the Sigil map pack. So anyways, okay, let's see. If the type isn't copyable, this is a compile time error. Interesting. Okay. The call passes. I guess it's just avoiding the copies and taking ownership or something when I'm doing that. That's the ownership model. So it's it's moving the value, so to speak. Okay. I'll have to read through this again. Okay. Now this one, the following code works by making a copy. Okay. So these were different, right? Because let's see here. This is passing a newly created thing in here. I see, yeah, because we don't have the transfer sigil thing there. But this example, let's see. Take text, hello. Okay, so that's actually mutating it because it owns it, prints the text here. That's fine, and then but it is just making a copy here, so we're just passing in the copy, I guess. Okay, so it's different. We get 2 different results here. And this version here, which when we take ownership of and print the message, it's going to give us the error, which we saw that previously in the first video here. Okay, nice, neat system here. Okay, so this is pretty cool. I think this is a neat and obviously well thought out ownership system. So 2 more things to dive into. There's a lot to dive into. I just want to see pointers. Okay, so it looks like there is a owned pointer, which maybe is a unique or shared pointer type of thing here. Oh, there's a bunch of different pointers. So safe pointers, nullable pointers, smart pointers, and then copyable types and so on. Okay, so quite a bit. And this is actually, again, just insightful. Again, just going to spend 10 seconds on this. But in C++, right, we added in C++ 11 3 types of pointers. Unique pointer, which kind of looks like what must be this owned pointer. What was it called? Probably something like this here. Owned pointer that points to an int value. Okay, I don't know. I don't want to make any claims about that until I study it more, but we have unique pointer, shared pointer, and then weak pointer. So 3 smart pointer types in C++ 11 and beyond. But there are many types of different safe pointers and types of pointers that you can have. So this looks like a nice list of things to read And again, nothing preventing you from writing your own additional types of smart pointers. So just want to kind of make that point here. And then it looks like we have unsafe pointers here, just basic. I guess it is literally declared as unsafe pointer. So, I mean, that's kind of nice, because then if you're going to grep through your code and search for this string here, you'll know, hey, maybe that's where the error is. Or, again, it's not that they're totally unsafe. You have to know what you're doing. Sometimes they're nice for performance reasons, but sometimes you also just need to interface with like a C library or something that's, doesn't have safe pointers. So that's totally fine. All right, let's get into the intro to GPU stuff here. And again, this is awesome documentation explaining what is a GPU. What are the different, it's a highly parallelizable machine. Let's just take a look at this. The left is your CPU, the right is your GPU, which has lots of these little cores here. They're usually like SIMD cores, and they work together. And they might be there might be another box around some amount of these that sort of work as a team of cores. I think that's what that's illustrating down here as warps, or what do they call them? Wave fronts on other architectures. But anyway, so they sort of work and execute asynchronously. But again, versus our CPU, which is very, it can do I/O and these other sorts of things and handle indirection and branching and so on. Our GPUs are mostly number crunching machines for the most part. So this is a nice introduction to GPU hardware. Let's see if we can get a basic little project here. Let's run just a little thing here. This is going to be the classic vector addition here. Let's just try to run some code here. I'm going to skip through it here. Because basically I just want to poke through this and see if there is, let's see here. I got a bunch of errors because I probably skipped something. Let's see, what did I do here? What did I do? I should probably copy the right project here. Let's see, check if a GPU is available. Okay, so let's see here. Let's see what error messaging we got here. Call expansion failed. Da-da-da-da-da. Did I just not piece something in right? Let's see if I could just use this example here. Nope, it is giving me an error here. We might just have to run this. Here, let's just see if we can run this in the playground. Let's see here. I don't want to mess with that too much here. We'll let run. And again, that'd be nice if they're giving us GPUs here in the playground. No compatible GPU found yet. Okay. But anyways, just looking at this code. Let's see. Okay, so compile time, right? We figured out what app parameter is. We're going to say if we don't have an accelerator, or if we do, find it. Okay, select that GPU and give us the name of it. Okay, simple enough. I wonder why that didn't work, but so that's sort of step one. Okay, we should find some GPU. Okay, now let's just take a look here. So typically when we write GPU code, you use something like CUDA, OpenCL, SYCL, some API that lets you write a shading language if you're in the graphics world code. And often for general purpose graphics programming, GPU, general purpose graphics programming unit, you write something called a kernel, which is like a function or a small program that is shipped off to the GPU and executes. So this looks like if I want to do a vector addition, I just can write out this little program here and compile and run it here. Okay, so let's run this program here. Let's do it in the playground again. Now I don't have a GPU here, so I wonder if it's just going to do this on the CPU and print the threads here, or it's just going to crash here. But what would it do? It would find our device, enqueue this function, so kind of load up print threads, and then take, let's see, I guess it's going to print out 128 things or something, a grid of 2 by 64. And then it'll synchronize and wait and then print program finished. Okay, and what's our GPU doing? It's just printing out the thread indices here. Okay, let's see how close I am on that. Description. Define a grid consisting of 2 thread blocks, each with 64 threads. I All right, and here's what it'll look like. It'll just print this out. That's pretty cool. And basically, this is a pretty simple, okay, this is basically where we need to get to end the video here, but I find a device, whatever it is, maybe a GPU, maybe an accelerator, or whatever. I enqueue some function that I want to call on it. I say, what are the, dimensions, 2 sort of thread groups with 64 threads. And then it's just a regular function here that I can effectively call here. And if you've done some GPU computing, again, this is telling you which thing is executing and on which thread, basically, right? We could see on the printout here. And again, they're not necessarily, although these ones are sort of in order here. Maybe they're synchronized, or maybe there's like an async function you can call or something. But that's basically it. So you're just off to the races here, which is pretty cool. Okay, so we're going to go more and more. So, I mean, the main thing I wanted to see is, am I basically just writing regular Mojo code? And that seems to be the answer, right? I've got some of these like special variables, that tell me which thread and so on that I'm executing on. But that's pretty simple here. So that's kind of nice. And again, kind of the whole purpose of this, language, as I understand it, to be able to migrate your Python code into something that's running fast, and just be able to write GPU programs for whatever task you want to do, AI, graphic stuff, simulation, etc., all in the same code base, from the same language, which is really, really neat, and make it easy to set up here. And there are other tools like, OpenMP and stuff. And again, various C++ libraries and APIs that let you write in C++, just C++ code and do this. But this is pretty well integrated here. It looks pretty simple here. Let's just see if there's anything else interesting that we should take a peek at. I mean, this is just showing more and more examples here and how to play around with some of the data. And actually, now we're actually doing a task here by populating our arrays and storing the results and so on. So again, nice little example here, kind of the classic vector, add 2 vectors of values here for the GPU stuff. So pretty cool here. And again, for folks who are more in the machine learning world, again, you'll want to look at these like matrices examples, I guess, or tensors, as we could say. Okay, so I mean, we think we covered a lot. We looked at a little bit of the interop here. We looked at the tools. We looked a little bit at let's see, the debugging. Hey, we didn't look at this too much, but they've got in their Visual Studio, Visual Studio Code a setup here, and I think I saw that right on the home page here. Yeah, VS Code getting set up here. So interestingly, for GPU debugging here, there are some, okay, so you can use like the NVIDIA toolkit on CUDA. So maybe it's using CUDA for part of this, or maybe you can use if you're on OpenCL or something, you can use that debugger. So it looks like you can set up some of the other debuggers there, because that's always one of the questions here, how to debug GPU code. You often need a different type of debugger here. Okay, testing, writing tests. Let's see, what's the last thing that we should do here? I guess there's just a test directory or so here that we have, write tests. And how do I execute? Oh, I just do test here, and then I can just execute the functions. Simple enough, very, very simple. I like it. Okay, so there's a full roadmap here. I mean, again, this language, as I mentioned, is, released. Maybe what I'm looking at is 4 months old and around 2 or so years. So early days, but, so I think there's going to be a lot of exciting developments coming here. We already talked about maybe classes, maybe interop with C and C++ world. Yeah, so it looks like there's an exciting future for the Mojo language. So I'll be really, really excited, really curious to see for folks who are working in this language what they think about, or other folks who have investigated it, what you like about the language, or similar languages where you've seen similar constructs, or other even APIs that maybe are of interest to the community that have done or integrated GPU programming nicely into your programming language of choice. In D, you have dcompute, and C++, you have a number of libraries that just let you write your kernels in the code. But Anyways, yeah, really, really nice language here. Again, there seems to be a good community. There's lots of talks and tutorials. Lots of open source projects already for a language that is this young here. So, so yeah, that's part two. We had to do a part two because we didn't even get to any of the interesting coding stuff last time, and even now we're just touching the surface. But if you've done some GPU programming before, you can see this is pretty much seamless. I mean, this looks like Python code if you didn't know any better, with some special variables telling you which thread and block you're executing on. So that's kind of nice. And it's also kind of comforting because hopefully it sort of tells you that GPU programming is not that hard. It shouldn't be, right? We should be able to get this speed. We pay a lot of money for these expensive GPUs, so we should be able to use them. So anyways, folks, with that said, if you didn't check out the first video, make sure you check that out, and hopefully you enjoyed this one. I had a lot of fun looking at the Mojo programming language. Again, it's been on my list for a long time, and we really got to dive into a lot of the compiler stuff in part one, and then part two, see the language, understand some of the things like traits, do a little bit more of a deep dive there, take a look at the ownership model a little bit, and there's a lot of goodies in there, and the GPU stuff. So really nice, clean language so far, and excited to see where it ends. So anyways, folks, with that said, thanks again for your time and attention, and I'll look forward to seeing you in the next one.